Asthma and Allergy Foundation of America reported that in 2024, over 27 million Americans suffer from asthma, a chronic disease causing inflammation and swelling of the airways.
Despite being one of the most common and costly diseases in children, the current responsive treatments such as inhalers, spirometers, and over-the-counter medications still leave asthmatics susceptible to irreversible scarring of the lungs from excessive asthma attacks.
This highlights the need for cost-effective and preventive solutions, shifting the focus from reactive care to proactive asthma management while keeping kids' needs in mind.
We are Kick Asthma, the group of students innovating a path toward this solution.
Focusing on childhood asthma, we work to create an assistive auscultation device for the lungs. Operating as a non-invasive technology, the device utilizes machine learning to detect abnormal breathing patterns before an asthma attack through a wireless microphone located inside the tubing of a stethoscope.
Externally placed on the chest or back, this technology would be paired with an easy-to-use app for asthma management and alerts, providing different alternatives for preventive care.
Through research and help from our mentors, registered nurse Peggy Dorsey and Dr. Emmanuel Cosiga, we have gained insight into the medical diagnostics related to asthma, attacks, and treatment methods. Striving to create the best quality of care for asthmatic children, Kick Asthma is taking auscultation technology to a new level.
Asthma is a chronic respiratory condition that causes inflammation and narrowing of the airways, restricting the flow of oxygen throughout the body. This inflammation is often accompanied by excess mucus production, which further clogs the airways and makes breathing difficult. As the condition worsens, the surrounding airway muscles tighten, a process known as bronchoconstriction, turning the simple act of breathing into a strenuous task.
When individuals with asthma encounter specific triggers, such as allergens, cold air, or physical activity, they experience an asthma attack, which is the sudden and severe worsening of symptoms. Although treatments like inhalers, spirometers, and medications provide relief, they don't prevent long-term damage. Repeated attacks can lead to the irreversible scarring of the lungs, a condition that progresses into what's known as airway remodeling. This permanent change in airway structure results in chronically narrowed passageways, reduced lung function, and a lasting impact on overall respiratory health.
In addition to the long-term health risks, the ongoing costs of treatment and the limited opportunities for preventive care make effective asthma management a significant challenge for many.
The question is, how can we make asthma care more effective, accessible, and affordable?
In September, we began by conducting targeted research. We looked into the factors of asthma attacks, current treatment methods, long-term health risks, and the financial burden on patients. This research informed our design direction and clarified where our solution could provide the most value.
We also conducted a detailed competitive analysis, evaluating the strengths and weaknesses of existing asthma tools. That process revealed key gaps in areas like affordability, portability, and real-time monitoring, shaping our vision and solidifying our goals of creating a more accessible, preventative, and cost-effective design.
With a strong research foundation in place, we shifted into a solution-driven brainstorming phase. Guided by our initial findings, we sketched ideas, mapped out customer needs, and explored a wide range of possibilities. Each concept was influenced by what we had learned, ensuring our ideas remained grounded in real-world changes.
This led us to the Asthma Assist, an innovative, non-invasive auscultation device designed to detect and warn about potential asthma attacks. With a 3-part prototype consisting of the device, implemented machine learning, and a user-friendly app design, the Asthma Assist uses continuous monitoring to identify abnormal breathing and alert the user of the issue.
In October, we shifted from concept development to validation and early design. To better align our work with user needs, we distributed a focus survey to individuals with asthma. The results showed strong potential, with 93.3% of respondents indicating they would consider using a technology like ours. However, while 87.5% expressed hesitation about wearing a device as adults, 100% said they would have been open to it during childhood. These findings not only reinforced the relevance of our concept, they also guided us toward a focus on pediatric users, where early monitoring can make a lasting impact.
From there, we brought our concept to life through technical 3D modeling. We broke the system into 3 key components: a stethoscope head to capture breath sounds, tubing for clean signal transfer, and a microphone to process respiratory audio. This helped us clarify design specifications and explore how the physical device could take shape.
At the time, our solution centered around a single auscultation device attached to a central location on the chest. We believed this would provide a clear and consistent read of respiratory sounds.
However, during our hands-on session with our mentor RN Peggy Dorsey, the clinical nurse program coordinator at Atrium Health, we learned that a more effective approach would be to place 2 auscultation devices on the lower posterior lungs. She explained that breathing issues can be isolated to one lung and that monitoring both sides offers a more accurate picture of live-time respiratory health.
This insight shifted our thinking and played a critical role in refining our design. It showed us how sensor placement could impact detection and helped us adapt our concept to better support both clinical goals and user experience.
We concluded Phase 1 by presenting everything we'd researched, explored, and adjusted over the past 2 months, not only showcasing our progress, but setting a clear foundation for the next stage of development.
In November, we continued deepening our understanding of pediatric asthma. We reached out to Dr. Emmanuel Querciga, a board-certified pediatric allergy and immunology specialist, who helped answer key questions and offered an expert perspective into how asthma presents and is managed in children.
We also explored Living with Asthma, a research-based book that offered valuable information into how children navigate the condition day to day. It helped us better comprehend the emotional, social, and practical challenges young patients face, giving us a more informed understanding as we moved forward with design decisions.
By the end of the month, we took our first major step towards physical development, constructing the initial prototype. We began by assembling the basic components, positioning the stethoscope head, integrating tubing, and wiring a microphone to capture internal sound. The goal of this stage was simple: prove that our design could reliably pick up breathing sounds in a controlled setting.
We followed this with early testing to assess sound clarity, consistency, and overall system viability. It wasn't perfect, there were challenges with noise interference and component alignment, but each round of adjustments brought noticeable improvements. By the end of testing, we had successfully proven the viability of our design, as the prototype was able to clearly detect and isolate breathing sounds from the diaphragm. This marked a crucial step in bringing our concept closer to a real, functional solution.
In December, we focused on validating our progress and gaining critical feedback. We presented our first working prototype to Ms. Dorsey, who affirmed the strength of our concept and reinforced the urgency of the problem we were addressing.
She also guided us on the correlations between asthma attacks, anxiety, and environmental allergens, insights that broadened our thinking and inspired new directions for our prototype. With a promising preliminary device and clear design direction, we were ready to move into the next stage of refinement and development.
In January, we turned our attention to optimizing the core listening components, researching and testing new microphones to improve sound quality while reducing the overall device size.
These changes marked the foundation for iteration 2 of our prototype design. We reworked our 3D models to reflect the new microphone configuration and conducted rigorous testing, which confirmed that our new design was viable and moving toward a compact, reliable solution. Drawing on Ms. Dorsey's insights about the influence of anxiety and environmental allergens on pediatric asthma, we also created our first technical drawings for the app.
At the same time, we prepared our business profile for Shark Tank. To sharpen our competitive edge and deepen our market understanding, we became certified in the Blue Ocean Business Strategy. This process led us to reevaluate current and past competitors, whose offerings focus on reactive asthma care and assistive technologies. These products often require external dependency, lack portability, and fail to promptly detect abnormal breathing, missing the crucial need for affordable, proactive asthma attack prevention.
Leveraging our evolving business plan, viable prototype, and extensive research, enhanced by our conversations with pediatric asthma specialists and other medical professionals, we defined the unique value of the Asthma Assist. Our solution not only eliminates expert dependency and delayed detection, but also reduces excessive medical appointments while raising factors like early prevention, portability, ease of use, and affordability. In doing so, the Asthma Assist creates a new market space for child-friendly designs and real-time lung monitoring in the pediatric medtech field.
In February, we shifted our attention towards making the Asthma Assist experience more engaging for our target users, children. We launched a new round of polling to gather input on app themes, and the results were clear. Dogs and cats were the most desirable with 38.5% of respondent votes. Using this data, we began creating visual models for a child-friendly app layout, thinking critically about both appearance and functionality.
As we shaped the app concept, we also revisited one of the core challenges: how to communicate alerts to children who might not have access to a phone. To solve this, we started exploring additional alert systems and landed on a vibration mechanism. This would allow the device to physically notify the child or caregiver in real time if abnormal breathing is detected.
To make that real-time detection possible, we began working on the machine learning model that would pair with our auscultation device, teaching it to continuously monitor breathing patterns and flag irregularities. This was a critical step in transforming our prototype into a responsive, intelligent system.
With growing confidence in both our design and business plan, we submitted the Asthma Assist to 2 major competitions, the National NoPro Social Entrepreneurship Challenge and the International Blue Ocean Student Entrepreneur Competition. These platforms gave us the opportunity to share our work on a larger scale and refine the way we communicate its impact.
To close out the month, we had a final meeting with our mentor, Ms. Dorsey. She affirmed the direction of our design, validated the viability of our second auscultation system, and supported the integration of app elements, reinforcing that our work was not only technically strong, but clinically relevant and meaningful for pediatric use.
In March, we finalized the visual design for the Asthma Assist app. While we have not yet built a working version, we have a fully fleshed out concept that maps how the app will look and feel. This completed design reflects our focus on making asthma management more accessible for kids, balancing functionality with the playful, child-friendly elements that we began exploring in February.
We also continued refining the machine learning component of our prototype. Using supervised learning, we trained a prediction model with approximately 400 audio files, half containing healthy breathing sounds and half containing asthmatic ones. We labeled 200 of these files to teach the system how to distinguish between the two, then tested the model by having it classify the remaining unlabeled files based on what it had learned. The outcome was a 93% accuracy rate in identifying asthmatic versus healthy breathing, an encouraging result that supports the reliability of our detection system.
To simulate real-world conditions, we engineered a creative test that we called baby surgery. Since we couldn't safely imitate asthma attacks ourselves, we inserted small speakers into 2 baby dolls, one playing asthmatic breathing and the other playing normal breathing. This setup gave us a controlled, physical way to see whether our machine learning could correctly identify and differentiate the sounds in a realistic environment.
Testing with the baby dolls was a hands-on way to validate how well the machine learning could process and interpret respiratory sounds. The results gave us confidence not only in the model's accuracy, but also in its ability to detect asthmatic breathing early, an essential step towards effective asthma attack prevention.
Finally, we received exciting updates from the competitions we entered in February. The Asthma Assist earned first place in the NoPro Social Entrepreneurship Challenge, and out of over 12,000 students across 163 countries, we advanced to the top 100 pitches in the Blue Ocean Student Entrepreneur Competition. These recognitions helped validate the strength of our concept and its potential to make a lasting impact in pediatric asthma care.
Now in April, we have completed the last step of our testing phase, evaluating adhesives for attaching the device to the skin. This was a key consideration for pediatric use, as we needed a solution with a strong, reliable hold that wouldn't cause discomfort or pull in the skin. Testing different options allowed us to identify adhesives that support both secure placement and user comfort during wear.
With this, we have begun preparing to share our work with a broader audience. Our first step was presenting at the In-House Expo, where we delivered a full overview of the Asthma Assist. It was a valuable opportunity to refine how we tell our story, consolidating 7 months of research, prototyping, and planning into a clear and impactful presentation.
As we go into Expo, we're proud to present a fully viable 3-part prototype, featuring a functional auscultation device, a machine learning model that can accurately distinguish asthmatic from healthy breathing, and a thoughtfully designed app concept. These elements represent months of research, testing, and collaboration, and together, they bring our vision for the Asthma Assist to life. Looking ahead, our next steps include coding the app, exploring manufacturing pathways, and continuing to improve efficiency and accuracy. The question was how to make asthma care more effective, affordable, and accessible. The answer is the Asthma Assist.